Hello everyone, good evening. Welcome back to our live discussion of AIATS Plus Phase 2 conducted on 9th of February. Right? And just like last time, we are going to be taking our topics forward from where we left off last time, right? If you remember, we were discussing ray optics, magnetism and matter. So we have some more good problems at our disposal. So I hope that you will find it interesting. So let's begin. So see here, today's topic for discussion. So I'm going to begin with, going to be beginning with two 11th class topics. Okay. They're both from your 11th class, and obviously the rest are from your 12th class. All right. So see here, this diagram, if you see, it's directly plucked from your NCERT, right? So whose diagram is it? If you guys remember, right? This blue line, please notice it, right? If you see these points, right? They are really special points. See these points. Why? Because see, this is a wave, obviously. I think it's pretty much clear, isn't it? But there are two other lines are also drawn. See, one is this dotted line, that's one wave. The another is this dark dotted line, that's another wave, right? And if you see this dotted line, right, this one, it is moving towards right, while this dotted line, it is moving towards left. So they are basically two simple harmonic waves, and they are moving in opposite directions, right? And what happens when two harmonic waves move in opposite directions? They are going to superimpose, right? And that superimposition gives us what? Which wave does that result in? That results in standing wave, right? That results in standing wave. So basically, right, these waves, these two waves I'm talking about, right? This wave and this wave, these two dotted lines, they are your harmonic waves, while this blue line indicates your standing wave. Now why do we call it standing wave, or let's say stationary wave? Because see here, if you see these special points, right, they are also called something. Why? You see this diagram has been drawn at different time intervals, right? So let's say this is t equal to 0, then after some times and so forth. But this point, if you notice, it is not rising. It is staying just like that there only, right? So it is undergoing no displacement, right? So this point, let's call this point as point A, right? Point A. So this point A has no displacement, right? And we call such points as nodes. Okay, nodes. And remember this blue line, I just now told you that this is your standing wave. You can, if you want, you can open your NCERT and check for yourself. All right. And these points are nodes. Okay. So if you have, how many nodes are drawn here? 1, 2, 3, 4, 5, 6. 6 nodes are drawn. And what about between two nodes? What do we have? We have antinodes, right? So which one are the antinodes? It is these points. See, this point, this point, this point. So what are these antinodes? Antinode is the point where maximum displacement can happen, right? Because at nodes there is no displacement, but at antinodes there will be maximum displacement, right? And one wave, we can call it as what? What would be one wavelength of this standing wave? It would be from, let's say, here to here, right? Or let's say from here to here. So that would be equal to one wavelength of the standing wave. So let me explain it in another diagram. See over here, same thing what I explained, right? You have nodes, right? Nodes. Then between two nodes you have the antinode where maximum displacement can happen, antinode. And let's say this is full length of the standing wave, but that is not equal to wavelength. Wavelength is, see here, this we can call it as one wave. So this would be one wavelength, right? And if I were to ask you, what is the distance between a node and an antinode? So what would that be equal to? So this distance would always remain the same, isn't it? So let's say if this is x, then this is also x, this is also x, this is also x, right? So 4 times x is equal to lambda, isn't it? 4 times x is equal to lambda. So how much distance would they be lying at? 4x is equal to lambda, x is equal to lambda by 4, right? That means this is the minimum distance between any node and any antidode, the minimum distance, right? And what about between two nodes? What is the minimum distance? Again, let's do it in the same manner. See here, this is node and node. Let that be x. Node and node, this is also x. And this constitutes one full wavelength. So x plus x equal to lambda. And that x would be equal to how much? 2x equal to lambda. X would become, let me write over here, node and node, okay? 2x equal to lambda. So that distance would be equal to lambda by 2. All right. So let's see. Let's see some good question from this one. Yes, good morning. Good morning, Pankaj. Good morning, Dasrath. All right, see here, a standing wave is produced by superposition of two waves. Just now I told you, right? Superposition of two waves of wavelength 20 centimeter, right? The distance between any two successive nodes, they're asking. So the wavelength is given. Lambda is given as how much? Lambda is given as 20 centimeter. And what's the distance between two nodes? Just now I told you, right? That distance would be equal to how much? Lambda by 2. So 20 by 2. And the answer is 10 centimeter. Right? Fair enough? Simple enough? All right. Let's go to another interesting topic, and you'll see we'll do some interesting question in this one as well. See, you have a block of mass m and it is suspended with the help of a spring, or in fact it is said suspended separately by two separate springs, and they have spring constants, let's say k1 and k2, and here what is given? The time period is given, right? So spring 1 time period t1, the next one's time period is t2. Okay, so let's write it in a diagram. So let's say these are the two separate springs. Here time period is t1, here time period is t2. So what would be t1 equal to? T1 is equal to 2 pi under root. Remember, for spring block system, right? The time period formula. One block of mass m suspended by one spring of spring constant k. 2 pi under root m by k, where k is the stiffness coefficient of this spring, or we can say spring constant. So m by k, and k is, let's say, k1 for this spring. And what about t2? 2 pi under root m by k2, right? So this one is your k1, okay? This one spring constant is k1, this one spring constant is k2. And if you go back to the question, they have also said if same mass is connected to series combination of both springs. So both springs, they are arranged in series now. Arranged in series, and now they are asking the new time period. So arranged in series like this, right? So here obviously I have shown the spring constants as k and k. Why I have drawn like that, I will ask you at the very end. But for now, let's say it is k1 and k2, okay? K1 and k2, and here they are asking us the spring constant. So spring constant, what would be the equivalent spring constant when both springs are attached in series, right? This formula you should remember by connecting it to, let's say, if you have studied electrical circuits, right? Resistors in parallel, right? So what was the parallel formula over there? 1 by R equivalent is equal to 1 by R1 plus 1 by R2, right? Over here, when they are in series, we will use that formula. So which means here, K equivalent would become how much? We would use this formula, 1 by K equivalent equal to okay. And here obviously they are asking the time period, right? So time period here, let's say t, 2 pi under root m, obviously only one mass is there, m, and in place of this whole spring, we can connect it with an equivalent spring of spring constant k equilibrium, right? So m by k equilibrium, okay, m by k equilibrium. Now what you can do, see from here, let's find the values of m by k1, only m by k1, right? So we can square both sides, right? t1 by 2 pi, bring it over here, then square both sides. So you will get m by k1, right? So m by k1 would be how much? t1 by 2 pi whole square, right? So T1 square by 4 pi square. Similarly over here, m by k2 is equal to T2 square over 4 pi square, right? But we are supposed to arrive over here, okay? See here, now how to find that? Let me write over here. So T is equal to 2 pi under root m by kq. Now kq, 1 by kq, use this formula, right? So let's say I'm multiplying both sides by m. It becomes m by kq, that is equal to m by k1 plus m by k2, right? So it becomes m by k1, okay, plus m by k1 plus m by k2. And here what you can do, just substitute these values, right? So what does it become? 2 pi under root m by k1, T1 square over 4 pi square plus T2 square over 4 pi square. Now 4 pi square, 1 by 4 pi square, you can take it as common outside the square root, and outside it will become 1 by 2 pi. The 2 pi will get cancelled. So what will remain over here? Under root T1 square plus, see here, plus T2 square, right? So which options would it be equal to, right? So what would be the correct answer? Okay, clear? Now here let me ask a simpler problem. Let's say instead of K1 and K2, the initial diagram that I had drawn, right? Let's say they are both K, K. So if they are both K, what will be the K equilibrium? You can use this formula and find out. K equilibrium would become K by 2. K equilibrium would become K by 2. And the original time period must be given. And they can ask a relation between this time period and the old time period. Such kind of questions can also come. But you have to employ the same method. All right? So I hope this one was clear to you. Let's move on. Now see, another question I have framed over here, but little simpler, or you can say a little equivalent to the previous question, but little different also. How? See, same block suspended in the same way to the same two different springs, and they're having the same time period T1 and T2, right? But something is different. What? Same mass is connected to parallel combination of both springs. So initially there was a series combination. Now there is a parallel combination. So if this is one spring, this would be the other spring, right? They have to be connected parallelly, not in a series manner. So in parallel combination, how would the diagram look like then? And again they're asking the time period, right? I will provide some small help to you, small hint, but this I'm giving to you as homework. See here, the same light, just like you wrote over there. Write the formula for T1, write the formula for T2, right? And over here you have two springs. The K equilibrium is different, right? So let's say one is K1 and another is K2, K1 and K2, right? And here they are asking the time period. So you have to find the time period over here. So what would you do? 2 pi under root, the same formula, m by K equilibrium. That formula remains the same. But something is different now. They are in parallel. So here which formula you would use? Try to connect it with the series combination of resistors, right? What was the series combination? R equivalent is equal to R1 plus R2. So here K equivalent would become how much? Let me write down. So here K equilibrium would become K1 plus K2. Okay, K1 plus K2. So now you can substitute it over here. 2 pi under root m by K1 plus K2. And this time period you have to simplify. And simplify and get the answer in terms of T1 and T2. Okay, so if you want I can again write T1. T1 is the same thing, what we wrote over there. T2 also the same thing. Right? T2 is also pretty much exactly. It's literally exactly the same. And if you want, you can, I will provide some small steps to you if you want. So T is equal to, what does it become? And before that, here, instead of finding m by k1, we wrote over there, right? Let's find k1 by m, right? So k1 by m, what would that be? If you see, k1 by m. Why am I doing k1 by m? I will tell you. K1 by m, that would be equal to t1 by 2 pi inverse and whole square. So 2 pi by t1 whole square. So that is 4 pi square by t1. Okay, and similarly over here, k2 by m, you can find out, that is also 4 pi square by t2 square, and obviously here also t1 square is also there, and that we have to find out. Okay, so now what I am doing, bring this m into the denominator, right? So what does t become? 2 pi under root, bring this m to the denominator, so 1 by k1 plus k2 upon m, k1 plus k2 upon m, that you can split it up into two fractions, right? Good evening Lakshay. See what it becomes, k1 by m, right? Wait. K1 by m plus k2 by m. K1 by m plus k2 by m. And now all you have to do is just substitute them. Okay. If you substitute them, you will get your answer. Alright. See this value, you have to substitute over here, right? And this value, you have to substitute it over here. Alright, you will get your answer. And if you want, you can check, right? You can check whether you are getting this t as t1 t2 upon under root t1 square plus t2 square. Okay, check. So again, this is mathematics now. It has less to do with physics and more to do with maths now. Okay, but I hope you found the physics part of it, right? How time period is related to mass and spring constant, because this topic we are doing it for the first time with you guys. And what to do when springs are connected in parallel, springs are connected in series. So I hope now it's clear to you. All right, so let's move on to our next topic. See here, another question for you guys. A particle is executing SHM, they have given. And what else is given? See, what is the mean position of this particle? Is that given? Yes, it is given, right? They are saying executing SHM along x-axis, So like that, it is oscillating, or we can say undergoing simple harmonic motion with origin as the mean position. So origin is the mean position, right? And velocity v is related with position x as this. Time period they are asking, time period of oscillation, right? So velocity v, what can you write it as in terms of x? What can we write it as? This we did last time, right? I had, if you remember, I had established a relation between v and x, right? So velocity v, it would be related to x as what formula, right? Omega times under root a square minus x square, right? A square minus x square. Now if you see over here, let's simplify this and see what it becomes. So 9v square is equal to, it is written, right? So v square is equal to what? Let's write down v square is equal to 1 by 9, 36 minus x square. Now what do we do? Take square root on both sides. See what it becomes. If we take square root, it becomes v is equal to 1 by 9 becomes 1 by 3, and this is under root 36 minus x square, right? And now if you just, all you have to do is compare, right? See here, v with v, under root x square minus a square would be how much? A square is equal to 36. So a is equal to how much? The amplitude, it is equal to 6, right? So the amplitude 6, I am writing it in SI unit, meter. Then omega is equal to how much? 1 by 3. Omega is your angular speed or angular frequency, and this would be equal to 1 by 3 radian per second, okay? Or you can write second inverse also. And from this, what all you can find? You can find the maximum velocity. Maximum velocity of that particle. That also you can find, but that's not what they're asking. What are they asking? Time period of oscillation they're asking. Time period, simple formula, right? Time period is equal to 2 pi by omega. Okay, this simple formula is also valid in the circular motion also. So this formula you need to remember. Okay, there is no excuse for not remembering this. This is fine. It's a revision today. So just put the value. Omega is 1 by 3, isn't it? So what would it become? 2 pi by 1 by 3. 2 pi by 1 by 3. 3 goes up. 6 pi. And what's the SI unit? 6 pi what? Second. So which one is the correct answer? This one? 6 pi second. Okay. And what was the another thing that I was asking? You can also find the maximum velocity. Okay, that is additional. Okay, let's say additional. Additional tip, that is maximum velocity of the particle. In that SHM you can find out. So what is that formula? That will be when it reaches mean position, right? At mean position, isn't it? And when is that mean position? At x equal to 0. That's already written. And Vmax, what is the formula? It is equal to omega into A, right? Omega you know, A you know. So just multiply them. It becomes how much? 2 meter per second. And it's very simple to derive also. See over here. V will be maximum only when x is equal to 0. So from that you are getting the answer. All right. So I hope this was clear to you. Right? Okay. So let's moving on to another topic. Now we have jumped into your 12th class, right? Diamagnetic substances, right? See here, so what are diamagnetic substances? First let's discuss some, and then we will go back to these symbols, because these symbols I introduced last time, if you remember. I didn't talk about diamagnetic materials, but I introduced these symbols, right? What is this one? Magnetic, susceptibility. And what is this one? Relative permeability, right? So if you see, this is the diamagnetic material, okay? And what does this susceptibility do, right? Susceptibility. What does it measure exactly? It measures how much that material is, let's say, being attracted to or being repelled by that external magnetic field. See, this material has been placed in external magnetic field, and if you notice, they are not going through the material, right? They're not going through, which means if let's say this material was attracting this magnetic field lines, so what would these magnetic field lines want to do? Obviously they would want to, it would penetrate the material, right? But they are not. That means it is not undergoing attraction. Actually it is being, we say, feebly repelled by the material, right? That is what we call as diamagnetic material, okay? So diamagnetic material right, it is feebly repelled by the external magnetic field, okay? So there is repulsion, okay? Feebly repelled, all right? And if you remember, we had talked some formulas, right, about magnetic field and how is it connected to Xi, right? If you remember, I had introduced the topic as we have a long solenoid, and in that solenoid we are placing a material, right? And because of that material, the net magnetic field would increase, right? Because you have magnetic field due to solenoid plus the additional magnetic field due to the material, right? But here, just now I told you that the diamagnetic material, it's not going to support, it's repelling, right? It's going to repel. So if you go back to last time, what was the magnetic field we wrote it as, right? We had written, if you remember, mu naught 1 plus xi into h, 1 plus xi into h, where mu naught is already you know, and 1 plus xi just now I told you, and h, what is it? Magnetic intensity, and h has a ideal formula which is n into I. N is the number of turns, okay, and I is your current that is passing through the solenoid, okay. N is number of turns per unit length, okay, not number of turns, okay. Anyway, if you want, you can substitute it 1 plus xi n into I, right, n into I. Now if you see, just now I told you it is repelling, which means it is not supporting. If it's not supporting, what do you think? Xi, what should that be? If xi is positive, right, let's say if xi is positive, that means we can say that the magnetic field inside the solenoid is increasing, right, because before placing that material it was mu naught Ni. Now after placing that material, we have got an increased magnetic field, because just now I said it is supporting, but here it is not supporting, it is opposing, right? If it is opposing, so xi cannot be positive, right? So xi has to be negative. Okay, so you can remember it like this, few things connect with it, and so xi is going to be negative. Okay, and how much negative? Very little negative only, not highly negative. So small negative value. Okay, you can write like this, small negative value, and xi remains constant with temperature. Okay, xi remains constant with temperature for who? For this material. We are talking about diamagnetic material only. So xi we can say is independent of temperature. Independent of temperature. So far I have explained to you why xi has to be negative. For a diamagnetic material, xi has to be negative. It cannot be positive. So it has to be negative, right? Now what does this term become? Because if you see in the question, there were something else also, isn't it? Xi we talked about. What about mu r? What is that one? Mu r is, how is that related to xi? If you see over here in that formula, right, this term is what we call as mu r. Okay, so that formula essentially becomes mu naught mu r n into I. Okay, n into I, and this whole thing as a whole we call it as magnetic permeability, and this is relative. So relative permeability, and this mu r is equal to 1 plus xi. Okay, and there is also a table that is drawn in your NCERT. If you see over here, this table, you can spot it in your NCERT. And for now, just focus on this one, talking about diamagnetic only. And xi, I just now told you, it has to be negative, right? It is going to be negative. So xi is less than 0, right? But what was mu r? Mu r was 1 plus xi. So xi is less than 0, then mu r would become what? Just add 1 on both sides. So what would it become? It would become less than 1, isn't it? 1 plus xi is less than 1, that is mu r. So mu r is less than 1. Okay, so please remember these two, xi is less than 0 and mu r is less than 1. Obviously mu r has to be greater than or equal to 0. I mean it has to be a positive quantity. Okay, and when would that be equal to 0? I will discuss just now in a few moments from now. Okay, and what about this one? How did this come about? Why is mu less than mu naught? Right, let me explain that as well. What was mu equal to, if you remember? Mu equal to, right, mu r into mu naught, isn't it? I just now I told you this is your mu. Okay, if you want I can write it down over here. This is mu into Ni. So mu equal to mu naught into mu r. So if mu r is less than 1, so multiply both sides by mu naught. So 1 into mu naught becomes mu naught only. So less than mu naught, and this becomes mu r into mu naught, that is your mu. Okay, so these three quantities we have discussed. Okay, so why they are like this, and last but not the least, what is this? Right, what is this? When does this happen exactly? When does xi equal to -1 or mu r equal to 0? Obviously, if xi is equal to -1, mu r will obviously become 0, right? But for which material, right? For which material? Okay, so please write down, we call it superconductors. Okay, and for superconductors we say that xi is equal to -1 and mu r equal to 0. Now what does that mean exactly? That means this xi is obviously, it is playing a opposite role. It's not supporting. that external magnetic field. It's not helping those magnetic field lines to penetrate the material, right? So what would happen in this case? Nothing will penetrate. That means everything will be repelled, right? So if you see over here, this diagram, I had drawn just one line, that is, see, penetrating the material. In case of superconductor, nothing will penetrate, everything would be repelled. So we also call it perfect diamagnetism as well. Okay, perfect. I mean perfect as in like there cannot be nothing, there cannot be anything more perfect than this one. All right. And yeah, one more thing, where are they used exactly? An example, right? So if you remember, magnetically levitated trains, right? Super fast trains. So they will employ this concept and this application. So it can find application over there. All right. Very well. Now see this question. This is also from your magnetism and matter. But see what is given over here. They said, right, a steel rod has a magnetic moment m and length L. So let me draw a steel rod. Okay, so let's say this is your steel rod. All right. And it has some pole strength on this side and this side, right? Some pole plus m minus m. So for now I'm just writing it as m. Small m is your pole strength. Magnetic moment capital M and length is capital L. So this length between these ends, it is capital L. So what would be the connection between them? Magnetic moment is your pole strength into the length between the two ends, right? Or you can call it the effective length if you want. Now what is happening? It is bent into a semicircular arc. So this whole thing, it is bending, right? It is bending. So what would the shape become? See, shape would become like this. So this end and that end, right? So let's say something like this. It is thin, all right? And here obviously you have the poles plus m and minus m, right? And it's a semicircle. That means it will have a radius, right? This will be the radius. Let's say r will be the radius. And now here they are asking the new magnetic moment, right? So here what will be the new magnetic moment? So here we will say the new magnetic moment m dash is equal to, the poles are pretty much the same only, right? So small m into the effective length between the two ends. So what is the length between them? Effective length, see, it is 2r. So you won't say this length, it is 2r. So effective length is 2r. So this is what you have to find out. Now how will we do this question? I think it's pretty obvious, isn't it? Again, simple mathematics. This rod we have bent in this shape, right? So if this length is L, this length is also L. And this obviously, remember, this is, if it were a full circle, circumference is 2 pi r, semicircle. So this arc length would be pi r. So this L would be equal to pi r, right? L would be equal to pi r. So what would be r equal to? R equal to L by pi. Substitute it over here. So 2m L by pi. So which one would be the answer? Right. So if you see, we have not yet found the answer. Why? Because this ml also has to disappear, right? What is ml equal to? See over here. Put it over there. So what would that become? M into L is capital M, right? So it becomes 2 capital M by pi. Okay, 2 capital M by pi. Now we have got the answer. Okay, this is our answer. All right, everyone, I hope everyone has got it. It was pretty simple, right? Just like this, we can make any question. So let's say instead of bending like a semicircle, I can make a triangle, a right angle triangle. So in that case, the effective length would be the hypotenuse. Okay. This was a pretty simple shape. If I had made an arc, that question would become complicated. All right. Moving on. Semiconductor, right? So last time I remember we had done one good question on semiconductor as a circuit, right? Forward bias, reverse bias circuit we had done. So today let's see It's a pretty simple basic question. See here, symbolic representation of photodiode they are asking, right? Photodiode they are asking. Now obviously this should be very simple, isn't it? Why? Because the answer lies in the option itself. They have shown the hint as well. How? See, photodiode means photo means light, right? So just like photocurrent or photosensitive material. So photodiode means it is going to capture light. So light is going to be falling on that photodiode, and what is that going to do? If you want, I can write down, right? Light, or we can say radiation, or we can say it is irradiated with light, falls on photodiode. And what is its purpose exactly? Its purpose is to generate current, okay? And it generates current because of this, right? And if you see the option, let me stand over here. If you see, there is only one option that pretty much tells you which light falling on it, right? Light means an arrow, right? See here, see here. So which arrow shows something falling on it? It is this one. Okay, you can remember it like this. All right, and this is it's an important optoelectronic device, which we also call it as. So I hope you have taken note of it. Anyway, see here, another this also you can say a simple question, right? Logic gate question. And if you see, two inputs A and B are entering, right? This logic gate, okay? And what is this one? What is this one called? If you remember, if it is curved like this, right, it becomes OR. If it is straight, it is AND, okay? So if it is like this, it is OR, and if it is like this, it is AND. If you want, I can write down, OR and AND, OR and AND. All right. OR means addition, AND means multiplication. So if you see, A and B are getting added up, right? I can write over here, add, this is multiply. Okay, so A and B are getting added up. So Y we have to find out, right? So Y is equal to, first A plus B, they're getting added up, and then this white circle has been drawn, which means it's a NOT gate. So NOT meaning we put NOT over there, right? You put NOT, then this thing is fed as the input to another. See here, it is another NOR gate. This is OR, but this whole thing is NOR, and this is another NOR, isn't it? So what would that become? See, A plus B bar is being added with A plus B bar. See, A plus B bar is added with A plus B bar, it is equal to A plus B bar only, and then a NOT you have to put over there. So which is basically nothing but, on this one you have to put a NOT. All right. So again a NOT. So what's the answer? It is A plus B only. Okay, or another way also you can do. This is NOR gate, this is also NOR gate. So NOR of NOR is simple, OR only. Okay. And if you see, check the options, which one is correct, see. Let's see this one. 0 plus 0 is 0, right? Y is equal to A plus B. 0 plus 1 should be 1, right? Which means this one is incorrect, right? This is incorrect. And here also if you see 0 plus 0 is 1, this is also incorrect. Here also 0 plus 0 is 1, this is also incorrect. Let's check this one. 0 plus 0 is 0, this is correct. 0 plus 1 is 1, correct. 1 plus 0, 1. 1 plus 1 is 1. This was pretty much the truth table for our OR gate. Okay. All right. Wave optics. Right. We have not yet entered this topic as well, right? YDSC. I had introduced a little bit of diffraction we had done last time. A small concept we had discussed. So what is YDSC, right? So YDSC stands for Young's double slit experiment, right? So 2 slits we are having. You see, one slit over here and one slit over here, right? And light is going to enter it from that side. Which light? Monochromatic light source. Now what does that mean? It means that light has a single wavelength. So if it is yellow, it will only be yellow, or blue, only blue. And if you see over here, that light enters and it is passing through those slits. See, from this slit it is going like this, and from this slit it is going like this. And some additional information is also given. See, this distance, capital D, has been given as much greater than small d. What is small d? Small d is the distance between the 2 slits. Now why is that important? See over here. If you see, if it is much larger, that means this screen, this is our screen, okay? The screen is placed very far away in comparison with small d. So that means these 2 rays, right? These 2 rays, what would be the path difference between them? Path difference as in the difference in their length, right? If you see, what would be the path difference? Well, all you have to do is drop a perpendicular, right, from this slit to this ray. And if you see this length and this length, right, they would be almost equal. So what would be the path difference be equal to? This length, right? And this length, it is written as d sine theta. Why d sine theta? Because see, this is a right angle triangle, and this angle, right, this angle is our theta. So d hypotenuse, this is perpendicular, d sine theta. So path difference, right, path difference delta x, right, it is the difference between the path length of this ray and this ray. So that's why I told you, you drop a perpendicular, this would become the path difference, especially because d is much larger, very far away. So delta x is nothing but your d sine theta. All right, and if you see here from the diagram itself, this angle is theta and also this angle is theta. See, this is another right angle triangle. Okay, this angle, huh? If you want, I can mark it again. See here, this angle, huh? This angle is also theta. So in this triangle, this is theta. So tan theta, what would that be? Perpendicular upon base. So capital small y by capital D, right? So tan theta would be small y by capital D. But just now what I told you, what would the theta be? Theta itself will be very small. Why very small? Because the screen again is placed very far away. This D is very large. So theta is going to be very small. That means tan theta and sin theta, they will be pretty much, they would have the same values. We approximate it as equal to theta. So tan theta, in its place we can write sin theta also. So delta x, what does that become? See here, delta x become d into sin theta. Instead of sin theta, we are writing this y by capital D. Okay, this is our delta x. And if you see over here, what is this white dark, what does that signify? What does that signify? See here, maxima and minima it signifies, right? Because remember I told you, these 2 rays, right, these 2 rays, they are going to superpose or superimpose over here. They are going to add up just like we did over there, right? In waves chapter, superposition happens, and what will happen? They will try to add up to each other or cancel each other. So if they perfectly add to each other, we call it a maxima, because their intensity is maximum over there. If you see over here, see this region, see, extremely bright, extremely bright. So which means there is a maxima. We also call it a central maxima. Okay, and then dark, that is your dark meaning minima, white meaning maxima. Okay, so which means at maxima what will happen? Delta x is equal to n lambda at maxima, and at minima what will happen? Delta x is equal to n plus half lambda at minima, right? So let's focus on maxima for now. So if you just equate them, right, equate them, what will happen? See, you will get dy by capital D is equal to n lambda, right? So what would y become? Y is equal to n lambda capital D by small d. So what does that mean? This was for, I said, maxima, isn't it? Maxima, if you want I can write it down over here. And this one was for your minima. So the n signifies which maxima it is, right? So let's say, for example, you put y equal to 3 or y equal to 4, right? It is 4 lambda d by small d. Or y at n equal to 3, it becomes 3 lambda d by small d. That means that maxima, okay, fourth maxima, third maxima, like that. So what would be the difference between the two maximas, or let's say the distance between the two maximas? So what is that called? The distance between the two maximas, that is y4 minus y3. What do we call it? We call it as beta, or if you subtract 4 minus 3, right? What does that become? Lambda d by small d, right? What is that called? That is called fringe width. Okay, that is called, okay, that is called fringe width. And similarly, you could have also done it by finding the minima. So nth minima, and then the next minima you find out, and then you subtract them. Again, you will get the same fringe width. If you want, you can try it. Very well. Now see this question. They have said Young's double slit experiment. The distance between the two slits is d by 3. Distance between screen is this. Wavelength is this. Find the fringe width. So directly we will use the formula for fringe width. Right? Fringe width we denote it by beta. Fringe width is how much? Lambda d by small d, isn't it? See here, lambda d by small d. Or let me write it as lambda dash d dash by small d dash. Right? Why? Because the lambda etc. has changed, isn't it? So in place of lambda, what will you put? The new lambda is 3 lambda. Substitute over here, it becomes 3 lambda. What is the new d dash? It is 3d. Okay, 3d. And what is the small d dash? That is d by 3, right? Distance between the two slits. That was d over there. Here I put d dash, and the d dash is equal to d by 3. Okay. D dash is equal to d by 3. Now if you solve it, 3 goes up, right? 3, 3, 3. It becomes 27, right? 27 lambda d by small d. So which one is the correct answer? 27 lambda d by small d. See, here you have to be very careful. These both look similar, but they are not the same. Okay? Very well. Now see this question, this it's a very simple question, right? And first of all, upon seeing the question itself, you have to, it has to come to you, like which topic it belongs to, right? It belongs to which topic? Obviously wave optics, because I have put this question under that topic, but in your NCERT it is given under Huygens principle. So please make sure you practice how Huygens principle is used to prove reflection and refraction. And if you see over here, when light goes from one medium to another, right? One medium to another. Let's say this is medium 1, medium 2. So what changes? What changes? Obviously, refractive index would be different, right? So let's say here refractive index is mu1, here it is mu2. Then what about wavelength? Yes, wavelength will be different. So here it is lambda 1 and here it is lambda 2. And what about speed of light? Yes, speed of light will also be different. Speed of light is v1, here it is v2. But what about frequency? Will frequency also change when it goes from one medium to another? Let's say it undergoes refraction, right? If you see, read the question. Light wave of frequency nu and wavelength lambda enters a liquid of refractive index 4 by 3. And the wave travels in liquid with, so the new wavelength etc. they are asking. And they are also talking about frequency as well, if you see over here. Because initial frequency is given as nu. So will frequency change? It won't change. Okay. So if initially frequency is nu, I'm writing it like this. Finally also frequency would be this only. Okay. This is your frequency. frequency is not going to change. And now how do we solve this question? So if you see, obviously that light wave is entering from, let's say, air to the liquid. Okay, so let me draw a new diagram for you guys. It is entering from air to liquid, air to liquid. Now here mu is how much, right? Here mu, for air roughly we say mu is equal to 1, and for liquid mu is given as how much? 4 by 3, right? So here mu is given as 4 by 3, right? And here roughly we can say mu is roughly equal to 1, not exactly 1 but roughly, all right? And what about the speed? Speed they are not talking about, they are talking about wavelength. But let's talk about speed as well. So here let's say speed is c, speed of light in air, and here speed we don't know, right? Here speed we don't know. So how will we do it? If you read the Huygens principle topic, all you have to do is see over here, mu into c, refractive index into velocity, right? You can remember it like this, mu into c, or mu is how much? 1. So instead of writing mu into c, you can directly write down 1 into c, okay? So 1 into c, 1 into c is equal to here 4 by 3 into v, okay? And speed can also be written as frequency into wavelength, right? Frequency into wavelength. So c I can write it as initial frequency was nu only, okay? So nu into initial wavelength was how much? Lambda equal to 4 by 3. Initial frequency was nu only, and final wavelength we don't know. Final wavelength we don't know. And by the way, even without solving you can see the option. This one would be wrong because frequency they have changed. So it is wrong. Wavelength, what would it be? And this is also wrong because wavelength has to change. So these two, between them we are going to choose the correct answer. So just solve it. Simple mathematics, right? You solve it, nu get cancelled, lambda dash becomes how much? Lambda dash becomes 3 goes over there, so 3 lambda by 4. 3 lambda by 4. And if you see the options, the correct answer. All right? All right. So we have entered ray optics, right? And in ray optics, we are discussing, if you remember last time we had talked about compound microscope, right? Big diagram I had showed you, right? Similarly, today we are talking about astronomical telescope. Today also I will show you a big diagram, but a small formula you have to remember, right? And in this one, the most important salient point you need to remember, right? Which is what exactly? That in compound microscope, if you notice, which lens was bigger, the objective or the eyepiece? Over there the eyepiece was bigger in compound microscope, but over here the objective will be bigger, okay? So you can write down objective is bigger. Why? To capture what? Light, right? To capture more light that is falling from a very, very far away object. So light itself is coming by difficulty, and there if you are, let's say, enlarging your objective, light will easily enter, okay? Because if the objective is made smaller, light will find it even more hard to enter, okay? So that is why objective is bigger. Objective is bigger means what? The focal length of objective will be greater than focal length of eyepiece. So please keep that in mind. This was not the case in compound microscope. It is exactly reverse, okay? I will show the diagram. See over here, there are two diagrams, very important diagrams. One is your normal adjustment, right? Normal adjustment means what? See here, the image, right? The image is formed at where? Image is formed at infinity. If you see, light rays are entering, right? Here they have converged, and then upon entering this lens, it appears that the light is coming from infinity. That means a virtual image, we can say, is formed, or we can say that the image has been formed at infinity. Okay, So in this case, what will be the magnifying power? So magnifying power, what is the formula? F naught by Fe, okay? F naught by Fe. So please remember this one. In normal adjustment, it is equal to F naught by Fe. And what is the length of tube? Right? Length of tube, it is L, equal to how much? See here, see from the diagram itself. If the light rays are converging over here, which means this should be your focal length of objective, right? And if you see from here, the light rays are never intersecting. That means this should be the focal length of eyepiece, right? So what would be the length of tube? F naught plus Fe, we can say. Simply F naught plus Fe. That's all. So two important formula, F naught by Fe and this one. Let's do a question. Quick question, very simple question, see. Length is given 80. Length of astronomical telescope is given 80. But just after seeing that, you cannot write this formula. L equal to F naught plus Fe. We cannot write this. Okay, we will write it only when it is normal adjustment. It has to be written. And is it written? Yes, it is written. So F naught plus Fe is equal to how much? 80 centimeter. Magnifying power is 15. So that means F naught by Fe is equal to 15. Now it is a simple calculation, right? F naught is equal to how much? 15 Fe. Put it over here. So what does that become? Simple maths. 15 Fe plus Fe equal to 80. It is 16 Fe. And Fe is equal to how much? 80 by 16. That is 5 centimeter. Okay. And what about, is that what they are asking? They are not asking focal length of eyepiece, right? Objective. So what would be objective? 15 into Fe. 15 into Fe would be how much? 15 into 5. Okay. Very simple. And this is the another diagram, second diagram. The even more than this, the formulas, right? This formula you can pretty much easily remember, right? So how I connected to you guys. So please remember those two formulas. And if you see over here, in this one, the second diagram, the image, the final image has been formed at near point. Near point meaning D. D is equal to 25 centimeter, right? Near point means you won't be able to see an object that is placed closer than the near point. Okay, so D is your 25 centimeter. Again, same F naught Fe they have drawn. And if you notice, F naught is much bigger than Fe. And also if you notice, objective is bigger than eyepiece. And here you have the magnification formula. Over there it was F naught by Fe. Here it would be F naught by Fe into 1 plus Fe by D. That's it. So if you compare, which one has more magnification? In this case only, right? Because over there F naught plus Fe, and here some additional term is also there. So in this diagram, when the image is formed at near point, the magnification formed by astronomical telescope will be more. Will be more. All right. And this question, if you see, you can take this question also as your homework. Okay, you can try on your own, right? And if you see here, the same, right? In the first case, normal adjustment is given, right? So magnifying power is F naught by Fe equal to 10. Second case, length is in the same case, length is given. So F naught plus Fe is 110. Magnifying power, now new magnifying power they are asking. When the image is formed at the near point. When the image is formed at the near point. So in the first case, you have to write two equations, right? F naught by Fe is equal to 10. F naught plus Fe equal to 110. You solve it, you will get F naught and Fe. And now, a new magnifying power they are asking when image is at near point. In this case, which formula you will use? That second formula which I wrote, right? At near point, that is F naught by Fe 1 plus Fe by D. Everything is known. F naught is known, Fe is known, and D is how much? Let me write it down as well. D is 25 centimeter, okay? So please keep that in mind. D is 25 centimeter. Huh? If you substitute, you will get your answer. Alright, so please check. If I am not wrong, I think the answer is 14. Okay, I think so. So you can check whether if you are getting the answer as 14. Okay, very well. The last question of the day. Last question. If you see here, prism, right? On one face of a prism, a ray of light is incident at an angle 60 degree. So angle of incidence they have given. So I is equal to 60 degree they have given. Okay. Then they have also said on one face of prism of refracting angle 90. Refracting angle. Now what is the refracting angle? Angle of prism. We did, if you remember that big diagram triangle I had drawn. So A is equal to 90 degree. Right? And they are also saying one more thing, if you notice carefully, this ray of light is incident so that minimum deviation is also happening. Minimum deviation, right? And at minimum deviation, if you remember, I will be equal to E, right? And R1 will be equal to R2, and their sum would be equal to A. So R1 equal to R2 would be how much? Equal to A by 2. A by 2 means 45 degree, right? And the deviation they are asking. So what was the original formula for deviation that we have derived? Delta is equal to I plus E minus R1 plus R2, right? Minus A. That's it. You just substitute the values, you will get your answer. You will get your answer. Now here if you notice, there was no need to do any other formula for deviation, right? With this formula itself, we are done with it. Because they have already said at this I only minimum deviation is happening. So this I has to be equal to E. So 60, right? So 60 plus 60, all in degrees, minus A. A is how much? 90. 120 minus 90. And that becomes your 30 degree. Okay. So I hope we had a good session, and I hope you found this session as well interesting. Thank you for watching.